No.
Oh, that's fine.
Sorry.
We can do it now.
Okay.
All right, so, I mean, if you need, we could, this is more open-ended, but we're excited to end the conference with a open problem session, which Nick and Michael have graciously agreed to also do double duty on this. We've compiled some questions from some of you and from some people at the Texas conference last week and other places, and yeah, and feel free, the audience should feel free if anybody has any other suggestions or ideas on any of these things. It should be a very open-ended format. Yeah. Sure.
Yeah, it's likely that we're not going to make it through all of these, and so if something turns into a discussion or you want to chat, like that's fine. You're not derailing anything. That's sort of the point. So,
And I guess we should say, start quickly, is that if we don't get through all of them, which I agree is likely, the slides will be posted on the website for the conference, so yeah, everyone will have access to everything. I also really quick want to say, I will probably have to step out just exactly as this ends, so I won't be able to stick around and talk with everybody, but it's been a wonderful conference, and I really enjoyed being able to come here and join with everybody. And so I think this is a really great way to end the conference, talking about new problems. And even if I don't get a chance to chat with you about these open problems, I think this is very much the spirit of why we have these in-person conferences, is this opportunity to talk about what we're working on and looking for new solutions and new ideas.
and maybe this is a good time to just thank the organizers. Cool. Do you want to take the first one?
Sure, I'll take the first one. Okay, so these problems, by the way, these problems are not Nick's or my problems, and so we might stumble on a few things. But anyway, these are some of the problems that have been presented that we're looking at. So this first one, we're talking about Ramanujan's congruences. I think these have come up several times over the last couple of days. So first of all, we have these congruences for 5, 7, 11. Sorry, okay, great. So Algren and Boylan proved that these are the only nice congruences of this shape. Okay, so a nice congruence means we're taking, like, so in this case, we've got a prime times n plus something else. There are other examples of congruences. Ono showed that there are lots and lots of these, but they all look kind of nasty like this. They're a little bit more complicated than just the prime times a parameter plus something else. They're not just linear in the same way with the slope being the same modulus.
I think that one hit once.
There we go. Okay. And so Radu proved that there are no linear congruences for partitions 2 or 3. Okay. So we don't even have any of these weird kind of nasty ones that Ono gave. However, we do have this, we've got this conjecture kind of talking about the behavior in these cases. So Subaru said that every arithmetic progression contains infinitely many odd and infinitely many even partition values. So we can't break it up into these ones are all even, these ones are all odd. They're just all, every one of these progressions contain infinitely many of both. But that doesn't answer the question about portions. We just know that there are infinitely many. Okay. So we have this theorem, Ono and Radu prove that Subaru's conjecture is true, but do these sets, do they break up into density 1/2? Are there some arithmetic progressions that change the density? Or can we say much of anything at all about the density? And I don't think that there are any, I don't think there are really very many results along that direction. So yeah, can we even show that the density for odd or even partition values is even positive? Okay. We've got the statement about this fundamental barrier. I don't know where that comes from though.
Well, there are many different ways to prove that the number of values up to x that are either even or odd or about x to the 1/2 plus epsilon.
Great.
Yeah, but that's even beat the 1/2 by a positive power, let alone get to
positive proportion. Right?
That, yeah.
I know that either the evens or the odds have a positive proportion.
Yes.
I can say that.
And the 1/2 has
Yes.
something to do with the existence of theta functions. Yeah.
So we can do lots of exclusion theorems to say that one or the other.
That's yes, but that's not very useful. Great. Okay, I think that's all on that problem. Oh, what can we, and then similar things, what can we say about partitions mod 3? Okay,
All right. Does anybody want to chat about this?
I have a question. So like, when you were defining, this sounds so dumb. So when you were defining like on the previous slide.
Yeah.
You said something about linear congruences for partitions 1, 2, and 3, like. I guess I don't,
so
when you say linear.
linear, so we've got
arithmetic progression.
In an arithmetic
so
progression.
something times k plus something else. Yeah.
Are there like, I mean, I guess all the congruence theorems I see are linear. Are there congruence theorems that are not linear?
Presumably, but the point, I don't know.
Are there statements like P of n squared plus 1 is congruent to something, not
there-
something?
There are some examples of some things are congruent to theta functions or something like that, where you get like square classes. I know of something
Oh,
like that.
okay.
There's
Alright,
like the
yeah,
log
so-
theta
yeah.
function, like they'll make a Frank's talks about it, but you can also get it from the board. Yeah, there's some others, but
Yeah, but they're not going to be these Ramanujan type.
that's another interesting question. There are no linear congruences. Are there any other kinds of congruences for partitions?
Akin has
Still
some
don't know.
quadratic congruences mod 13
Oh,
in the partition function.
Other-
Like there's 0 on a quadratic curve.
Yeah, I was just mentioning that I think a result by Anna is also that like P of maybe some n squared plus 1 over 24 or something contains infinitely many even part. So the partitions of infinitely many of those elements that sort of quadratic sequence is even or odd if there exists one. So it's sort of partial, right? So you'd have to compute one of them, then you would have it.
That's right. And yeah, that's what the hard part wants to do. The problem shows that there always is. one.
Yeah.
But I guess I'd like to pose that open problem then. Are there any interesting congruences of any type modulo 2 for P of n?
So I think this would be an interesting question, no matter what you can say about this modulo 2 or modulo 3.
Is there like any computational evidence?
Yes, it's computationally instant.
So Scott and I, with some undergrads at Illinois, we looked at the sequence of zeros and ones that you would get if you just reduce P of n mod 2. And if you think of that as a binary number, it has all the properties of a normal number. So like every sequence that you could possibly imagine in the right number of they appear the right number of times. Like it's as random as you could hope that it would be. So my guess would be there's nothing whatsoever, period. It's just completely random.
If there's some chat.
Oh,
Oh.
quite a bit in the chat. Technically, we still don't know either set has density, so we don't even know the joking at least one has positive proportion.
Well, at least one of them has a positive.
At least one of them has to, right?
That's a joke, but yeah.
Parkin and Shank studied this, that the number seems normal. Yeah.
What would like being normal imply about this? Would that just be an observation, or would it have concrete?
It tells you that it's as random as possible. There's basically, you don't have any hope of finding patterns that are going to persist.
Every finite sequence shows up with proportion equal to 1 over the length, basically 1 over 2 to the length
Equal to or in the limit.
in the limit.
Yeah.
But like,
I mean, does the limit rule out the quadratic type stuff now?
I think it probably does. I think if there's any structure at all, like that has no hope of being like that random. But I don't know, maybe not. Maybe quadratic stuff doesn't mess with it too much.
Exponential.
Well, there exists some sequence because there's like the sequence of numbers for which P of n is odd. Plug in, so there's some.
All right.
Like a log law.
Any other comments?
This is a little bit tangent, so it's not about mod 2 and mod 3, but I guess something I've been curious about, if you have, say, mod 5, where you know that, yes, you're gonna have this lower bound for what's divisible by 5. If you exclude the ones that are in these arithmetic progressions that you know are gonna be 0 mod 5, is the rest of it equally distributed? Because at least it looks that way to me.
Yeah, we did some computations about that too, and I think the answer is yes.
Okay, I'd be happy to hear more.
Well, I mean, I don't know how to prove it, obviously, but
So, I mean, take this with a grain of salt, but at one point when I was a graduate student, Ken said he did know how to prove that kind of result.
okay.
And that it's true for like primes other than 2 or 3.
Oh.
So yeah, you can throw out the Ramanujan congruences and what you expect this like that equidistribution should be true.
Oh.
And he said he had, maybe I shouldn't throw him under the bus, but he said something like
You are being recorded right now. so-
yeah, he said something like, I think I know how to do this.
Oh.
Yeah, I'd like to think. Well, I don't think there is any paper. Yeah, so.
Yeah, certainly computationally, it's definitely true. Oh, another one up there?
Yeah, forgive me if this is maybe a naive comment, but I guess, so at least for the question of mod 2, the first thing that comes to mind when thinking about this question is, well, let's go to potentially combinatorial type discussions, like way to look at it. And there are potentially at least 2 different ways you can try to, you would try to know if something is even or odd. The first is counting the number of self-conjugate partitions. That will tell you whether or not that will tell you the parity of the whole thing, because the ones that aren't self-conjugate cancel out. And another possibility is counting the number of partitions where so once you take out a free square and you consider each like leftover part, if those 2 are the same size, then counting when that happens is also a way to get parity. Both of these have all right generating functions. I mean, the first one is Chi's is one of Ramanujan's name functions. Don't know about the second one.
I mean, many modular methods have been tried, and I think you're gonna get the same barrier. It's really the.
Yeah, that should give you a congruence between modular forms.
You have to get rid of the poles and end up on void space or something in some way. And there are things, I still, it's an interesting idea, but I think that you will encounter the same fundamental barrier for the same reasons.
Doesn't notice congruences P of AN plus B mod 5 suggest that the remaining P numbers are not equally distributed mod 5?
So I think that's what.
Yeah, throw those.
They're not 20% mod 5, but they're a little bit more than 20% because of that. But once you account for that, then we expect it's the random proportion.
Yeah. This same question was posed, and I remember at least Ken saying.
Oh, the remaining, yeah.
He knew the answer. So maybe I misspoke.
Oh, I see.
don't think the answer is-
Okay, so okay, what I think is true is once you take out whatever you need to take out, like whatever is sort of like known to be divisible by 5. If you take that out, then everything else should be equidistributed. Like that.
Yeah.
So talking about, infinitely many divisibility properties by 5, or infinitely many
If it's co-prime 6, then it's
that doesn't necessarily mean equal distributions, right? Because that can be a small number still.
Yeah, that's gonna be sparse.
Should we move on to the next problem? All right, so the rank of a partition is the largest part minus the number of parts. This is a measure of failure of symmetry of the Young diagram across the diagonal. So you can start with something with rank 1, and then the conjugate will have rank -1. So we'll define n of m sub n, m comma n, as the number of partitions of n with rank m. And then similarly, n mqn is the number of partitions of n with rank congruent to m mod q. So there's a theorem that if you count the number of partitions of 5n plus 4 that are congruent to k mod 5, all of those sets or all of those numbers are the same. And this explains the Ramanujan congruences, at least mod 5, and similar thing for ranks mod 7. So yeah, this explains the congruences mod 5 and 7 in a combinatorial way. And Dyson conjectured that there was probably another function that explains the 11 congruences called a crank. And this was defined by Andrews and Garvin in 1988. And it's defined that way. Of course it is. And the theorem is that the cranks explain the Ramanujan congruences mod 5, 7, and 11. So I want to move this out of the way. Elementary fact. The equidistribution for cranks mod L on a progression Ln plus beta is equivalent to something. The divisibility of the q to the ln plus beta term of, I think this is the crank generating function, by a cyclotomic polynomial. And I believe elementary fact means you still have to look at it, because maybe it's not clear from what's written here, but
Yeah, you could give it to a Gregor.
okay. Elementary.
Well, basic.
That's like the same kind of thing that Frank was talking about.
That's right, yeah. And I think this elementary fact has to be in Garvin and Stanton. I think we didn't find it explicitly stated there, but they're like using that idea.
Yeah, I mean, yeah, it's implied, yeah.
Okay, so question of Stanton. Ranks and cranks distribute partitions into equinumerous sets. Can we find a direct bijection? Stanton notes the divisibility of, and I stared at this for a while, and I think this means R or C, not R divided by C. So I got it, I figured it out. If you look at the q to the ln plus beta term of the rank or crank generating function, the divisibility by the cyclotomic polynomial. If the quotient had positive coefficients, he suggests that they may count something important. This doesn't work directly. Not sure what this means, but that's okay.
If you try it, it's false. The coefficients just are
They're not positive. Okay.
Wait, what function?
So you divide, so we know that the rank and crank work to explain these conferences. They are, for example, if you look at L equals 5, you 5 and plus work. Those are all visible by the 6 cyclotomic polynomial. And when you take that quotient of that coefficient by that cyclotomic polynomial, Stanton thought perhaps that if the resulting thing has positive or non-negative coefficients, it may count.
Yeah, I thought you meant R divided by C, and I was like, but I get it. Yeah, divided by the R.
It's R or C. Yeah.
But that's the only.
I guess
thing
that's
on the
like
slide.
the symbol in that.
That would have been worse. Writing the word or would have been probably better.
Actually, that zeta should be in C.
What's that?
The zeta should be in C.
Zeta.
Yeah, because you've got a coefficients, a polynomials in C,
Zeta is e to the 2 pi I.
and you want the cyclic polynomial to divide those.
Yeah, we're taking the crank as a function of C and tau, so C, the zeta is e.
Nothing's
The
defined, so.
the rank generating function is a power series in Q, and the
Yeah.
coefficients are polynomials in C. You factor those polynomials for that coefficient Q to the ln plus beta, they'll be divisible by the corresponding cyclotomic polynomial in Z.
Well, we have a different, we define rank as a function of tau and although it is also a function.
It doesn't make sense. Sorry.
Well, it's a different dimension.
Okay, so for some definition of these letters, this is true.
Just think there might be a type of P and C and zeta, they're supposed to be the same.
Yeah,
Yeah, the zeta should be Z.
here, and here.
Yeah,
Well, those are exponential forms and those are the.
Yeah,
arguments
so
of
Q
exponential.
is-
The Q is e to the 2 pi I tau, and the zeta is e to the 2 pi I.
no. You forget the e to the 2 pi. These are formal power systems in Q with coefficients that are polynomials in Z.
So all we're saying is if you take it as a formal power series. with
And what you're doing is you're taking each one of those coefficients, it's a polynomial, you're dividing by another polynomial. You'll divide it, and when you divide it, what you've got left over is a polynomial with non-negative coefficients, if you do it right. That's all it's saying. I mean, that's the
Okay.
evidence that we have. I mean, did you prove this?
In the case of cranks.
Right, but it's just a question about polynomials.
Yeah.
In my opinion. I don't know what you
But
didn't
it's,
prove that. I don't know.
you
what
have to
proved.
study the inequalities of these, study the inequalities of polynomials of two variables at the same time. The range may be moving in two directions simultaneously, and that's a really hard thing to estimate in a analytic way with explicit error terms.
Yeah, I don't know. Well, I believe that.
Where does the expansion talk about this? Is the paper?
So I believe there's a stand on his website as a PDF called something like problems.
We presented these conjectures at Roosevelt's.
But I don't think that
Yeah, well, yeah, there is an official paper, but he does have a file on his website.
So just to be clear, L is just 5, 7, or 11 on that
Yep.
side?
Okay, so here we're defining a modified rank and crank. In terms of these. Okay, well, you can see it. And the conjecture is that all of the following things are Laurent polynomials with non-negative coefficients. So these modified ranks and cranks divided by the corresponding cyclotomic polynomials that should divide.
Oh, that's okay. As long as you use the same variable in the numerator and the denominator.
All right. Theorem, the crank part of Stanton's conjecture is true. What about for ranks? What do the positive numbers mean for cranks? So Larry, can you say why this is hard for ranks, but doable for cranks?
well, it essentially boils down to we boil it down to unimodality questions. If you like look at the table, all of the ranks are cranks, you need to look at the rows and show they're eventually unimodal. And why you need to modify them with these 4 additional terms is if you look at these tables, for example, for ranks, the tails on the left and right are always 1, 0, 1. There are never any partitions. There's always one partition of rank n and one partition of rank minus n, but there's no partitions of plus or minus n minus 1. So the 1, 0, 1 at the tails is not unimodal. So you just so Stanton basically just deletes those ones and shifts them towards the middle so that problem goes away. And for cranks, it actually, the hard part was actually already done by others, by Q series methods. But we can't say anything about, we can't modify that proof for ranks, and we can't say what the numbers mean because it's a long and difficult paper with many difficult Q series transformations, and then just a comparison of this Q series has bigger coefficients than this. And so you can prove they're positive essentially, but you can't say what they really mean. And for ranks, that Q series method is very delicate. And for either ranks or cranks, we don't have an analytic method to understand, to prove that it's positive. We can do it in very short ranges, but we just can't prove those. We don't have the technology to prove those kind of unimodality type results in 2 variables for 2 variable generated functions like this.
Cool. Let's see. Does anybody want to chat about this anymore? Questions or comments about ranks and cranks?
I can mention one.
Yes.
There are these congruences for the SPT function, SPT mod 5, 7, and 13. So me and Andrews, the student, have a crank function that explains the mod 5 and 7 congruence, but we have nothing that will explain the congruence mod 13.
Huh.
So it could be one of those things.
That's for the SPT function.
That's for the SPT.
Well, that's a great open problem. Yes, I didn't remember this. I didn't.
And those,
It's
and the
still-
SPT crank is actually related to the rank in the crank. Believe it or not. It's the rank generating function minus the crank generating function, and you divide by something. But it doesn't work. It's because the rank. Yeah, the rank is weird mod 13, and so is the crank. But the SPT function, it's weird that there's something true. It's an open problem.
So since the crank is already the word used for one that only explains 2 of the 3 congruences, if someone finds one that explains SPT mod 5, 7, and 13, what do you suggest they call
Frank.
it? Oh, I said last week if somebody gets one for something with Frobenius partition, then we should call it Frank.
Does the SPT crank, is it only defined in like a generating function sense, or is there a way to think about a combinatorial?
Yeah, the Bill Chen School in Tianjin in China have an explicit combinatorial way of describing. I mean, me and Andrews and Liang just did the generating function, but they were able to interpret it. Not easy. I mean, just to prove those coefficients are non-negative is not true.
All right, let's move on. You want to take the next one?
Sure. Okay. Yeah, so we have this this conjecture of I don't know how to pronounce this. Is that Canada and Russell? What's that?
Canada.
Canada. Okay, so we have this conjecture of Canada and Russell on these partitions of n. So if we're looking at partitions of n, so that I assume this means that every part of the partition is congruent to plus or minus 1 or 3, odd 9. Okay, and this is equal to the number of partitions that satisfy this other conjecture, where we're looking at the difference of consecutive terms.
Sorry, I wrote this
So,
really poor slide.
so this is like, if the difference is small, then there's some congruence condition.
Yes.
Okay.
And then there's a second condition that the difference separated by 2 has to be larger.
So the second condition is supposed to always be true,
Yes,
and then the first condition is an if this, then this one.
yes.
And you can tell because the typesetting is slightly to the left of the implied sign, so it's not actually part of
I
the.
apologize.
It's fine.
We're just
It's
giving you a
also-
hard time here. It's all good.
Yeah. It's also like, I looked at this before and I still wasn't entirely sure what to make of it, but it's also kind of a complicated conjecture. But yeah, so we've got this conjecture of these sets of partitions satisfying these properties. And so I guess, yeah, so these would correspond to the following identities, which so we're I assume what we're saying here is on the left-hand side, the coefficients of that give
That's the second one.
oh,
Yeah,
on the
so-
left-hand side,
The
you do the
left-hand
second
side is the second one. On
and
the
the
right-hand
right-hand
side
side gives you the first one. Yeah, there we go. I see that.
The right-hand side looks like a Rogers-Ramanujan thing.
Yeah.
Oh my God.
Well, this looks like a Rogers-Ramanujan type identity, right?
Yeah.
Kind of a sort of more
Yeah.
complicated version of that, but this is kind of a combinatorial way of interpreting a sort of Q-series identity, right? And so our remark, this is a sum product identity, like a Rogers-Ramanujan type identity. And then I guess there's a connection to level 2 affine Lie algebra characters, which
Yeah, maybe I should, since you can't read my mind. Yes, I think there are probably people here that know a lot more about this than I do. But this is one of many Q-series identities that Nade and Russell found essentially, I think, by a computer search.
Okay.
And some of them have been proven. I think this one has not. And so, yeah, I guess me personally, I was interested because I think these sum to product identities are really beautiful. And you can interpret, or I guess one of the ways they search for these is you can guess, I think that, or I guess I think that the sum side is known to be a character for a level 2 affine Lie algebra. I believe in this case, it's associated to the A9 system. So the 9 shows up there as well. And yeah, I think in general, we have a lot of these combinatorial things, and a lot of them have been proven kind of as a case-by-case basis. And it's a little mysterious just how to prove things like this in general, if they're very difficult. So,
Yeah.
yeah, I think this is yeah, and this is a very beautiful and relatively simple identity. That's kind of, I mean, it's not too old, but now 7 years old. Yeah.
Yeah, so I have a paper co-authored with Ole Varner, and he did a lot of these types of things with the algebra characters, and I don't understand that part of the paper at all. But lots of those identities, those types of things opt out. And this looks kind of similar to some of his stuff, but a little bit, just a little bit different there for sure. Yeah.
But the proofs of the other conjectures, as far as I understand, don't use this like the algebra types connections. You know, it's like Q series, manipulations, modular forms, failing pairs, that kind of stuff.
So Varner's, I mean, in that one paper, he did a lot of more complicated stuff. They used some of the Lie algebra stuff. There's some of these identities and lots of variables, and then you take lots of limits and different variables and stuff, and things collapse. But yeah, I mean, he didn't get this identity. This one's definitely different, and so
Apparently there weren't enough variables.
apparently.
I will say, so one of the things the Lie algebra structure can add is sometimes you do have these more variables, and kind of in the background, there's this root system running around, and you have this the like vague group of the root system. And so a lot of these identities are invariant under action of that. And so that reduces, if you suspect you're in a finite dimensional space, that kind of shrinks that space even smaller by adding another thing condition. Yeah, that's one way I think it's been useful in some instances, but I think mostly it's used as a way to maybe search for conjectural identities.
Yeah, well, they're definitely very, very beautiful identities. I look at something like that and I love the identity. As far as my ability, I'm mostly equipped to be able to tell you something about special values on the right-hand side. But yeah. Do we have any more thoughts or conversation about this type of stuff? People would approach these types of proofs.
I don't want to discourage anyone, but like my impressions from hearing about how people talk about these conjectures is like, okay, so the conjecture that I proved this out earlier today, like that's a conjecture that somebody wrote down in 2007, and then I think like between 2007 and today, I don't think anybody's really like thought about it. You know, I think that's why I was able to prove it. I think. But these conjectures, smart people have been trying really hard to prove.
So don't even try.
No, I'm not telling you not to try. I'm telling you, if you can do this, lots of people will be really excited.
That's why you should do it.
Yeah.
That's why you should work on something.
Sure. Well, and I think maybe the answer, at least part of that might be like there's certain obvious approaches that are probably not going to work. People have already tried a lot of the obvious approaches. You're probably going to need some kind of back approach that's going to maybe use something like the affine Lie algebra somewhere in there. It's likely that there's going to be some complicated identities in multiple variables that you've got to manipulate, because those are the types of proofs that prove these types of identities in other situations. And so there's going to be a certain amount of background work that's you're going to have to go into it. So yeah, I mean, not that you shouldn't try, but recognize that there's going to be a certain amount of work. And if you don't already know how to do some of these things, probably expect to invest a certain amount of effort into learning some of those techniques.
So Drew Sills has a recent book on the Rogers-Ramanujan identities, and there's lots of different techniques for looking at these things. Just to plug his
Yeah, it's an excellent book. I know that book. Yeah, that one right there.
And then get it.
Yeah.
Yeah, I have a question. Someone mentioned, I forget, that this was conjectured because of a computer search. Can anyone elaborate, or whoever said that, can you elaborate a little bit on that?
I believe it was, no, I guess, I don't know how exactly that went.
So I mean, I would say it's somewhat straightforward to write down the sum sides from the difference conditions. And then it's very easy to find an infinite product that matches with your sum up to however many coefficients you want. There's an algorithmic way of doing that. And so that's what they did, basically. As I understand.
Oh, so there's
They played with these difference conditions and then used sort of recurrences and explicit Q series to compute the first 1500 coefficients, and then it's very easy to check on the computer whether that's a nice simple product.
I mean, Frank has a package for this.
I'm not sure about the sum side. The sum side is the hardest one. There's congruence property, the congruence condition immediate. But the sum side generating function associating the part difference condition and then the sum multiple sum generating function is not. So I don't quite remember. It was quite a long time ago the conjecture came out. So which one was first? I don't remember. But probably the difference condition first, and then she formulated. Some people formulated some side.
Yeah, I'm sorry. Yeah, I misspoke. So yeah, Kanata and Russell have some papers where they work out this how to do the sum sets in some cases, and the work of Khan.
Right, those people work
recently.
on actually to
Yeah.
figure out so that you can know what the identity we are looking at is true. So just we have only the description of our condition we are looking at without the multiple sum generating function is really hard to prove. We don't know what identity we are looking at. So the first step was actually to formulate the identity, and then the next step is but that one is still out there.
And I would point out in very general contexts, things like things of the shape of the left-hand side in general, you can try to, there's a lot of work on this, norm-type sums and things like that, which are connected to many deep things, but you can often tell that things like the left-hand side should be modular, although you can't really, you can't see the difference right away unless you look at multiple cusps. Like from this point of view, you see Mach modular forms, and you also discover Mach modular forms at the same level, sort of like how Ramanujan was investigating things like we talked about. But it's often very hard to know by looking at the radial asymptotics like we saw in some of the earlier talks on Mach theta functions. And you can, in the sea of Q hypergeometric series, the modular and the Mach modular thing really stand out as having very distinguished asymptotics that are very easy to calculate. You see right away that it should be something modular. And then a lot of the times those modularity results, the only way we know how to prove it is by connecting it to some infinite product like that. But so this might help you computationally discover many examples among many Q hypergeometric series that should have modular type representations such as the right-hand side, but this doesn't show you anything really about how to prove these things. But there are interesting ways to try to find these.
So proving this would help prove modularity of the left-hand side, is that?
My guess would be you can't prove the modularity of the left-hand side unless you prove this identity.
Yeah.
Or at least this would probably be the easiest way to do that.
I would,
if you could probably say modularity, it's just you're essentially gonna find a check.
yeah. George has a really nice survey or memoir also, which asks about taking things like the left-hand side and proving that they're modular directly without proving sum equals product identities. That would be like the dream in this stuff, but typically we can never prove modularity unless you prove some identity.
Just a lack of tools, other kinds of tools that would approach that. Anything else, or should we move on?
Do you want to take the next one since you have to go?
Yeah, okay, I'll take this one and then I think I'll step out after that. Okay, so this one then, is this a new one?
Yeah.
Okay. Okay, so I don't think I've seen this one before, so
We're sorry for springing.
we're gonna jump into this. Okay, so we've got a Q series here. So little v1 is our generating function, and the coefficients are capital V1.
This is George's notation.
So it's really good notation.
Interesting. Okay, and so this is defined by the series here in the middle. Okay, yeah. So a similar, I mean, kind of a similar shape as what you saw in the previous example. Sort of thing that we kind of see often in sort of modular Q series identities. So combinatorial interpretation. So OE is the number of partitions of n in which the parity of the parts alternates, and the smallest part is odd. Okay. So let's see. So the rank of such a partition is necessarily even. Capital Vn is the number of odd even partitions of n with rank congruent to 0 mod 4 minus the number with rank congruent to 2 mod 4.
Okay. So this is kind of like how f of q counts even rank minus odd rank.
Okay. Yeah. So odd even, that's going to count all of these that satisfy this property, and then V1 is going to restrict this further, right? Am I understanding that?
Yes,
Okay.
yeah.
Okay. So we're counting these particular partitions with all of these conditions here. So Andrews conjectures 1986 that the absolute value of this goes to infinity as n gets large, and that for almost all n, 4 consecutive values are going to be 2 positive and 2 negative. Okay. And then for n greater than or equal to 5, there is this infinite sequence such that any 3 consecutive values in here all have the same sign. Oh, not 3 consecutive
Yeah.
Three
yeah,
consecutive starting
Within-
at
okay.
those.
within this.
Yeah, there are infinitely many counterexamples to come to. It's essentially what I'm saying. And the n starting at 5 is just because he also conjectures the size of capital N, so it makes the notation.
Okay. Okay, and so this is some subsequence of these, and we're looking at consecutive terms within the subsequence. All of those have the same sign. Okay. Let's see. So Andrews also gives functions v2, v3, and v4 with similar conjectures. Okay. And I assume those are going to have similar types of shape like this.
Yes, they all have similar shapes, and I think I don't know if you write it down, but I think they also have computational interpretations.
Okay.
Yeah, I guess I should say I got this. I wasn't aware of this conjecture. It was suggested to me from a colleague in Cologne who did some computations, and as far as I'm aware, like almost nothing is.
Interesting. Do we know anything about these functions themselves? I mean, this looks similar to sort of the left-hand side of some product identities. Do we know anything about any of them having product forms or anything like that?
I have a guess where they might come from, but I have zero evidence for that guess, so I don't want to say.
Okay,
Yeah.
it's fair enough. Okay, so this is that's a kind of surprisingly old open Q series conjecture.
We just kind of wild last. Something that, I mean, it's like a little bit different, but a little reminds me of this Andrew's first conjecture on sigma.
So this appears in the same paper that he makes. So yes, my guess is that it should this behavior should somehow come from a similar place. Is that sigma function is connected to some quantum modular things, or Moss waveforms, which we might not have time, but are discussed later. But then George was able to prove the sigma conjectures, and I don't know if it's because he couldn't prove this or he just decided not to. So I don't know if maybe a similar solution exists.
Do you think that, I mean, so I guess like most concretely what you're proposing is perhaps there's some indefinite data series representation or something. Do you think, I mean, that's a indefinite data series, and that's a big search space. Is there any more computational way to run through that?
I think that these, if I had to guess, again, no evidence, I think they come from probably some Hecke character or a real quadratic form. And there's probably some nice Bailey pair or something or other that gives you this cubic geometric thing. But again, this is like 50-50 if that's even close to right or not. But that's kind of what happens with the sigma case, and so these look and seem to behave somewhat similarly. So I think they're a slightly worse case. Maybe than the sigma case. That's what I would guess.
Well, I don't know if we're gonna have time to get into it later, but maybe you could imagine, like Swagers has this alternate theory that I don't think many people use or many people know about because it's only been cited a few times, where there are things that are slightly worse than sigma in a very particular way, and they're kind of like Mach modular forms, but it's a different like alternate universe of Mach type objects.
Isn't that the next thing?
Oh, maybe it is.
It's
no.
the thing after.
It's the thing after this.
Which well, this one has already been shown. So, yeah, so maybe that's a good thing.
We did start a little bit late. I don't mind still going. Michael has to go.
Okay, I do need to head out, but thank you again for the conference, and sorry for stepping out.
Thanks, Michael. Think about time. We gotta clean up a little bit after we gotta go to dinner. It's like if my baby can go to sleep on time. Maybe we could go till 5:15.
Yeah, that's fine.
Or we can get there.
I mean, we'll just see. I think we started about 10 minutes late, so if we want to go 10 minutes more than. Okay, so strongly unimodal sequences, rank of strongly unimodal sequences. So there's that. There's a theorem that the generating function for strongly unimodal sequences of size n and rank m is that, and it has the following indefinite data series representation. And this is going to connect to some of the stuff that we're just talking about. So the problem is to determine any sort of modular properties of these, I lost it, it's gone, of these generating functions, either u or I guess u multiplied by the eta function. And then this one, this was the most interesting thing to me, which is why I kind of wanted to keep going a little bit. This one I think is really cool, because I know nothing about it and I would like to learn more about this. So there's a parallel theory to the indefinite data functions of Zweger's thesis and Mach modular forms. So there's this example, sigma. If you change signs from this plus to a minus, then you get a 6th order Mach theta function of Ramanujan.
I should say it's not just this example, that sort of thing holds in general. If you have a Mach theta function with this kind of representation, you can flip the sign and get a nice quantum modular form like sigma and vice versa.
Nice, cool. So Zweger's gave a general construction of Mach Moss theta functions. Okay, so maybe the thing to talk about here is if you take in this sigma, correct me if I'm wrong, but if you take sigma and you replace q to the n with the thing that shows up in the Fourier expansion of a Moss cusp form. So like a k-Bessel, it's like a k-Bessel function. You just replace all the q's with k-Bessel functions for no reason whatsoever.
Well, Zagi does have it, or Lewis and Zagi do have some stuff where. Okay,
I'm
so
sure
the
there's
map
a
from-
reason.
the
I'm
map
making a
from
joke.
Exponential of x times k-Bessel function to q to the n is an integral over a closed Green's form of the form. So
Okay.
it's a formal mapping.
Yeah. Whatever. It's 5 o'clock.
You repeat that one, you replace what, the x?
You replace q to the n in the Fourier series.
Yeah.
You replace all your q's with the k-Bessel function that shows up in the Fourier expansion of a Moss cusp form.
If you do that for sigma, you get a Moss form.
If you do it, yeah. So if you And you don't, and so you replace it with the K-Bessel function associated to, if you had eigenvalue 1/4. So normally this is like 1/4 minus.
Right, but it's not of the same Laplacian, right? So this must be eigenvalue 1/4 must not be the normal Laplacian, right?
No, I think it's the regular Laplacian, the weight 0 Laplacian.
So the Moss waveform is the more natural thing to start with.
Right,
That's kind of
yeah.
backwards. Yeah, so Swagers gives a way to construct Moss waveforms of the shape that do have some properties. And then, yeah, there is a way to show that replacing that with Q to the n is not so unnatural.
But Alex, I guess the reason for this too is Ramanujan in his lost notebook wrote down that Q series. And then George noticed that the absolute values are going to infinity, but there's infinitely many zero coefficients in the middle. So it has this strange behavior. And then what was eventually proven by Andrew Dyson, Dickerson, and Cohen is that if you do this operation instead of Q, you just put in these K-Bessel functions, that sum is a Moss waveform, or well, it's half a Moss waveform. It's the positive coefficients of the Moss waveform.
Yeah, okay.
Yeah. Okay, so there's a general construction for a mock Moss theta function. Yeah, so when you do this replacement, then the thing has the eigenvalue that you would like, but it's not modular, it's almost modular. But to make it modular, you can complete it by adding instead of a non-holomorphic part, some other integral of something.
I mean, so it must be, yeah, like, so that makes more sense, right? Because we know that the lowest eigenvalue, weight 0, normal Laplacian is like 91.19. This is.
Sure, yeah, so it can't actually be, well, I mean, is this on SL2Z?
Well, it's got a hectic characterism. No, it's not on that.
Yeah, so it's some higher level, and so for a higher level thing, you can have eigenvalue 1/4.
Yeah, right. I mean, these are kind of dihedral forms.
Yeah.
Explained by these, like the eigenfunctions sitting at 1/4, like kind of have this Galois. Yeah, so that makes more sense. Okay.
Yeah.
These actually also transform differences.
Everything does.
God created the Bayes representation and alphabets.
All right, yeah, okay, so instead of being an eigen, okay, so when you complete it to become modular, like you would with a mock modular form, it breaks the eigenfunction property, but when you apply the Laplacian minus 1/4, you get cusp forms times conjugate, complex conjugates of cusp forms. And so you replace the condition holomorphic with the condition having eigenvalue 1/4, and you also have these like period integrals.
I can just say a quick word. Yeah, so like in the ordinary harmonic cross form situation, if you're familiar with, right? Like you start with these indefinite theta series and a Euler series of things that are the Q series that are holomorphic, and you add some, and holomorphic is the same thing as in the kernel of the C-op, the shadow operator, or the lowering operator, however you want to think about it. And then you get things that are no longer in the kernel of that operator, but when you apply that operator, instead of getting 0, you get something, in a lower dimension, easier space than what you started with. For example, an ordinary modular form. And if you have mixed mock, which we saw come up in some talks, instead of just getting a modular form, you get like modular forms times conjugates of modular forms. And in this case, instead of the lowering operator, instead of the shadow operator, the analogous thing is delta minus 1, the shadow operator.
Pretty cool. In some special cases, the completed thing is equal to the original thing, so it's modular and has eigenvalue 1/4. And this was the result of, I guess, Lewis and Zagier, several other people. And I guess the question is, what else can we do? Maybe this is a good place to stop.
Yeah.
Maybe I'd stress one other thing. I guess what we one obvious direction with what else can be done is, right, what about the case where those special cases where that is equal? And
I can say that they have a really cool way to prove that these things are there's a natural automorphism group of symmetries, and you can apply this. So actually, the completion term that you add is not just, it's actually a difference of two functions, and there's a group of symmetries acting on those functions. And so being a Moss form in the completion being a Moss form, like in the sigma star case, but we don't have sigma star, is equivalent to those two functions being equal. And basically that typically happens because there's some special symmetry. And a lot of times you can see this represented in, and this also happens in like higher depth, indefinite theta, higher depth modular form, indefinite theta functions. Whenever you have some extra special symmetry on the quadratic form, like maybe if it's a diagonal form or it's SN symmetric or something, when there's a lot of extra symmetry, those symmetries can force these differences to be zero. And it's kind of a magical theory that just can you can even take infinite families of examples. You can take many, many examples of things that you suspect are related, are Q epigeometric forms that give Moss forms, and it just gives a system to just systematically just knock them out and prove that they are, which is super cool and actually pretty easy to apply. That's really good about Cypress work.
All right, so I think this is probably a good place to stop. We're all getting tired, so maybe let's just be done.
Right, let's thank you. Slides and particular others, such as Bernard Heim wrote more slides, and we did not have time to get to maybe even most of them, but everything will be, all of the questions will be posted on the website. So. All right, and everybody in the Zoom, thanks for joining, and see some of you later.